Hey everyone! You ever stop and think about how your phone just knows what you're going to type next? Or how Netflix is just uncannily good at picking your next binge watch? Well, that's all machine learning. But here's the secret. It's not some kind of dark magic. It's really just a recipe. And today, we're going to open up the cookbook and walk you through it step by step. So, let's get started.
All right, let's kick things off with a question that seems simple on the surface but is actually incredibly complex. Take a look at this house. How much do you think it's worth? Go on, take a guess. This is exactly the kind of problem that machine learning was born to solve.
Now, your first instinct might be to, write some code with a bunch of if-then rules. But you'd get tangled up so fast. I mean, think about it. Is the location more important than the square footage? What about the age of the roof or the number of bathrooms? The list just goes on, and all these things interact with each other in complicated ways.
And this is where machine learning just completely flips the script. Instead of us trying to spell out all the rules, we do the opposite. We just give the computer a massive pile of data, say thousands of house listings with their final sale prices, and we tell it, you figure it out. You find the hidden patterns. You tell us what really matters.
So how does a machine actually learn? Again, it's not magic. It's a recipe. A really clear, step-by-step process that takes us from a jumble of raw data to a smart, useful decision. Let's break down that recipe.
Okay, here's the basic workflow, the 5 main steps. First, we define our question. Then, we get our data ready. Step 3, we split the data. 4, we train the model. And finally, 5, we see how well it did. We evaluate it. Now, all these steps are important, but I'm going to tell you right now, one of them is way more important than all the others. And it's probably not the one you think. It's step 3, splitting the data. This is the absolute key to the whole thing.
In fact, you can think of it as the golden rule of machine learning. The entire foundation of this whole process rests on one single principle: an honest, fair evaluation. Absolutely no cheating.
And we do this with something called a train/test split. It's pretty straightforward, actually. We take all our data, and right at the beginning, we slice off a piece, usually about 20%, and we lock it away in a metaphorical vault. This is our test set. The model is never allowed to see this data while it's learning. The other 80%, that's the training set. These are the practice problems, the study guide the model gets to work with.
Just think about it like you're studying for a big final exam. If the professor gave you the exact test questions and answers ahead of time, sure, you'd get a perfect score. But did you actually learn the material? Of course not. You just memorized the answers. That test set is the final exam. It's full of questions the model has never seen before, and that's the only way to get an honest-to-goodness measure of what it truly understands.
Because if you break this rule, you run into a catastrophic error called data leakage. This is what happens when information from your test set, those secret exam answers, somehow leaks into your training data. When this happens, your model looks like an absolute genius during training. It gets everything right. But the moment you show it new, real-world data, it completely falls apart. Because it didn't learn, it just cheated.
Okay, so we've followed the golden rule. We've split our data to prevent any cheating. Now it's time for the fun part, actually training the model. This is the piece of the recipe that does the real learning. For our house price problem, the specific task we're doing is called regression. It sounds kind of technical, but it's just a fancy word for predicting a number. Any number that can be on a continuous scale, like a price or a temperature, or maybe next quarter's sales figures. It's one of the most common and useful types of machine learning out there.
So when we say the model is learning, what is it actually learning? Well, it's learning the importance of each feature, each piece of information about the house. It does this by assigning a weight, or what's called a coefficient, to each one. So for example, it might learn that adding one bathroom adds, say, $20,000 to the price, while being an extra kilometer from the city subtracts $5,000. It's literally figuring out what matters and by exactly how much.
But, and this is a big but, there's a trap. The training data isn't perfect. It's messy. It contains the real underlying patterns, what we call the signal, but it's also full of random quirks, weird one-offs, and irrelevant details. That's the noise. And the model's biggest challenge is to learn the signal without getting fooled and memorizing the noise.
So if your model is way too simple, it underfits. This is like trying to predict house prices using only the number of bedrooms. That's it. It's just too simple of a rule, and it's going to be wrong most of the time, not just for new houses, but even for the ones it trained on. Then you have the just right model, the Goldilocks model. It's complex enough to capture that true underlying signal, but it's simple enough that it doesn't get sidetracked by all the random noise.
This is the model that generalizes well, which is just a way of saying it performs almost as well on the brand new test data as it did on its practice problems. And then there's the big one, overfitting. This happens when the model is too complex. It gets obsessed with the training data. It doesn't just learn the pattern, it memorizes every single detail of the training set, including all that random noise. So yeah, it gets a perfect A+ on the practice data, but because it memorized noise instead of learning the real signal, it completely bombs the final exam, our hidden test set.
So how on earth do we stop our models from overfitting? Well, we use a brilliant technique called regularization. You can think of it as a penalty for being too complex. It's like putting a speed limit on those weights or coefficients we talked about. It keeps any single feature from having way too much influence, and it forces the model to find a more balanced, simple, and realistic pattern.
Now, regularization comes in a couple of different flavors. Some types, like Ridge, they kind of gently shrink the weights of all the features, which makes the model more stable overall. Others, like Lasso, are a bit more aggressive. They can actually shrink the weights of unimportant features all the way down to 0, effectively kicking them out of the model. But the goal is always the same. Create a simpler, more robust model that's focused on the real signal, not the distracting noise. All right, so let's recap our practical recipe. First, remember machine learning is a workflow, a process, not some magic black box. The most important step? Always split your data first to avoid that dreaded data leakage. No cheating. The biggest danger you'll face is overfitting, where your model just memorizes noise. Enter a secret ingredient to fight that: regularization. So we'll leave you with this final thought. The best model isn't the most complicated one, or the one that gets a perfect score on the practice test. It's the most reliable one, the one you can trust on the final exam. And that kind of makes you wonder, what other recipes in our own lives, our own work, could really use a more honest test?